Hi everyone, can you hear me?
Hi, Indra.
Hi, Agria. Can you
Hear
hear
you.
me?
Yes.
Cool.
Shall I start?
Hi, Monica. I think we'll be waiting for 2 more minutes and we'll go through a brief intro about SciPy India for another 2 minutes and then we should be in a position to start. Thanks.
Oh, okay.
Yes. Hi, folks. Thanks for joining the SciPy India community call number 2. I am going to briefly describe what SciPy India, these SciPy India calls and what SciPy India is about. And then we'll start with our first presentation for the day. So this might be a quick recap for those who have already attended the previous call, but SciPy India is a community of practice. And a community of practice is basically a group of people sharing a common interest, a common set of problems, a common concern. And communities of practice focus on sharing things like best practices, creating new pieces of knowledge to advance a domain, in which, in this case, that's scientific computing. And we are trying to do this to gauge, to not only build a sense of community, but also to gauge if there is enough interest to revive the SciPy India conference series. So these community calls allow a bunch of enthusiasts in the scientific computing ecosystem to basically share their research, talk about open source packages they have written or use, and how they're using them, and how the use of free and open source software can help advance their research and development practices. And similarly, we are also on we have workshops in the pipeline. We are trying to see how we can best fit them in an online format and also offline formats at different places. So this is mostly it about SciPy India. It's a very diverse, interdisciplinary community, and we're glad you were able to join. So I think we should be at a good position to start because we have set up our live stream already. Monica, if you would like to start your presentation, please do. Thanks.
Okay. So, hello everyone. I'm Monica Dhyani, a PhD scholar in the Department of Mathematics at Shiv Nadar University. Today, I'll be presenting my work titled Understanding Online Innovation Networks Using Network Science Approach. This work has been carried out under the supervision of my advisor, Dr. Satya Mukherjee. So, here is an outline of my presentation today. So, I will begin with the motivation behind this work, followed by the introduction. Then I will highlight the open source tools and packages that I have used in my work. Then I will explain how I use the key network metrics to do the analysis of the network. Then I will explain in detail what my work is all about, how I have done, incorporating all that, followed by the methodology adopted. Then I will present some statistical results. Then again results and what are the impact of the results that I have obtained, acknowledgement, and then I will wrap up with the references used in my work. So I begin with the motivation behind this research. So for that, we need to understand what online innovation networks are. So online innovation networks are platforms where people from all around the world, they connect, share ideas, solve problem together and learn from each other. Platforms like Stack Overflow, GitHub, and open source networks exemplify this idea. Now, what makes online innovation networks inspiring? So, first of all, global connections are created by bringing together all the people with diverse perspective. They promote knowledge sharing by making learning available to all by overall making learning available to all by collective knowledge, and they solve problems, complex problem effectively and efficiently. So when I explore innovation in digital platforms, Stack Overflow stands out as one of the most important as well as perfect example. So Stack Overflow is a community question answering forum where users ask questions and they receive answer from their peer around the world. So Stack Overflow is currently one of the most prominent and active community question answering forum, which was uh, introduced or launched for primarily for software developers and programmers. Since its launch in 2008, it has grown tremendously. Now hosts 20 million questions. So receives and receive answers from its peer around the world in the platform. So for the particular post, the user who asked the post is an asker, and all those users who are answering that post are the answerers for that particular post. So there can be multiple answers also, and every post is labeled with a tag. There can be multiple tags also, and these tags describe the topic it is related to. And so in a Stack Overflow, users can vote also. So as per the usefulness of the vote, they vote. If a user finds the post to be useful and well explained, the user upvotes the post. And if the user finds the post to be unclear and not useful, then the user downvotes the post. And on the basis of this upvote and downvote, reputation score is calculated. So it is given on the basis of upvotes and downvotes. This is the difference of upvotes and downvotes. So one of the major, or we can say important feature of Stack Overflow is that an answer post can be selected as an accepted answer by the by the asker. So the answer that best explains or best addresses the issue, that answer is selected as an accepted answer by the asker. And Stack Overflow also recognizes the efforts and the contribution of its users for reaching a certain milestone. So they are given different badges also as per their contribution. So gold badge is the most it is the very most difficult to earn, and it has the criteria how it can be earned. So represents high level contribution and the most difficult to earn, that I have already told. Awarded when a user gets a total score of 1000 from at least 200 answers. Then comes silver, which is comparatively easier to get and earned by scoring 400 from at least 80 answers. Then bronze is the easiest one to get and is granted for a score of 100 for it, at least 20 answers. So this is how these are the things there in the Stack Overflow. These are the features. And let's see how the Stack Overflow posts are organized in the platform. So at the top is the question post that you can see. At the top is the question post, and which is labeled with the different tags. So here we have 4 tags. And on the left hand side can be seen the voting interface, where you can upvote, downvote as per your as per the post is useful or not useful for you. And below the asker, this question post are the series of answers submitted by the users in the platform. And at the top, among those answers, also at the top appears the answer post which has been chosen as the accepted answer, and can be seen that it has been highlighted by the green check mark. So this is how a Stack Overflow interface looks like. And every post is accompanied with the user's details also, like user's name, user's badges earned, as well as post timestamp. Timestamp is the time at which the post was created. So these are the things that you will get to see there. So now let me walk you through the open source tools and packages used in this work. So Python has been the primary programming language for my project, widely used in data analysis because of its large community support and availability of powerful libraries. So it provided the environment to uh, integrate all my analysis steps seamlessly. So firstly, so I used Network X library to build users collaboration network from Stack Overflow data and to calculate important network measures. Then I used CSV module, Python module, which I used to handle CSV files. It allowed me to efficiently read and write structured tabular data important to store results. Then globe module I used to handle multiple files together because I was already dealing with multiple GML files. So it kind of helped me a lot. Then pull down parcel, I had a very large sized XML file. It was almost 104 GB large file. So it had to be handled like properly and without overloading the memory. So I used pull down parcel. It extracted all the information required in my work only without overloading the memory. And then os module, it's again a built-in Python module. This provides function to interact with the operating system. I used it to automate file path handling, directory navigation, and it could it led to smooth execution of scripts across different folders. So this is how I used all these packages and libraries. So data was prepared by using XML DOM. I parsed my XML files and I constructed network and network modules. Network metrics also were computed using this network X library for all 2023 to 20. This was these were the years of observation where studies based on like 2021 to 2023. So after computing these network files, um, so all these network metrics were like updated in a separate GML file. So I got 12 GML files. In this way, for 3 years, I got 36 GML files. So that way, and then I extracted user attributes like reputation scores, number of accepted answers, and badges also by using these modules that I have already discussed. Then by with the help of Stata, I conducted panel data analysis where I employed negative binomial regression because my dependent variable is count data, which is reputation score, that I'll be discussing in later slides in detail. Uh, Now, beyond just using open source tools, what really stood out were the advantages they offered for my research. So, these are freely available, cost effective, and continuously updated by a large community. They allowed me to process massive, like complex data sets across the multiple years without memory overload. I could handle extremely large XML files efficiently while systematically working with hundreds of CSV and GML files. So overall, these tools made the entire network analysis flexible, reproducible, and efficient. So I could like effortlessly do my analysis, all thanks to these modules and packages. So let's move on to the key network metrics that I have used in my work. So degree centrality is one of them, which represents the number of direct connection it has with, like a node has with other nodes, which is given by this formula where n is the number of nodes in the network. Local clustering tells ki how well or how tightly connected a user is with its, like how tightly connected the neighbor of a node R. So this is what it tells. So Ci equals to 2ei upon ki minus 1, where ki is the degree of node I, and ei is the number of edges between the neighbors of node I. Then strength of node I, it refers to the sum of weights of edges between I and j. Strength given by this formula where wij is the weight between the nodes I and j, and ni is the neighborhood set of I. Neighborhood set are those nodes which I is directly connected to. So that is the neighborhood set. Then is the K-core decomposition algorithm that gave me the K-core index for a node. So I have used 4 in total key matrices, key network matrix. So one of them is K-core index, which I got from like K-core decomposition algorithm. So how it works, it partitions the network into layers from center to the external ones. Low K-core value reflects the nodes in the periphery, and high K-core value reflects that the nodes are in the innermost core. So here I explain what my work actually is. So objective of my work is to investigate the influence of users' network embeddedness captured through structural metrics and non-structural metrics are all the network metrics that I just talked about, like degree centrality, strength, clustering coefficient, and K-core index. And non-network metrics are the number of accepted answers badges that we'll see later, number of number of accepted answers badges, and activity. on innovation productivity, which is quantified by the reputation scores within the Stack Overflow. So now let's see how I formed the network. So this is the collaboration network. So these are, so nodes are the users in the Stack Overflow platform, and if two users are co-answering, or two users are answering the same post, then there is an edge between them, then there I formed an edge between them. So this is how the network was created, and the weight corresponds to the number of times they co-answered a post. If weight is equals to 2, it means they co-answered 2 posts. Now let's see what variables are there. So I have so dependent variable that reflects the innovation productivity. So it has been denoted by TIT, where TIT is the reputation score of user I at time T, or T is the month here. Time is as per month. Independent variables are strength, K core, local clustering, degree centrality, that we already have discussed. And control variables are non-network attributes, or we can call them user attribute. Gold badges, number of accepted answers. Activity is the duration between users first and the last post. So methodology adopted is that firstly the data was collected. Firstly, it was downloaded from Stack Overflow data dump. For 3 years we downloaded the data, and these so total of 59 million something posts were accessed, consisting of 24 million question posts and 35 million answer posts. And the data in raw form was in .7z format, and it was extracted into a .xml format. After that, network was constructed, degrees and its network metrics were computed for all 2021 to 2022 month wise. Then these were updated in single GML files. Separately, those files were maintained. Uh, After that, user attributes were extracted and were integrated together in the single CSV file, again by using all those modules that I have already told. So then I did correlation analysis also, since I was already dealing with so many variables altogether. So I had to make sure that if there are some variables which are correlated to each other, because if there are variables which are correlated, then to capture the independent effect of one variable into onto dependent variable becomes difficult. So we had to make sure that there is no correlation. So correlation matrices were computed. So correlation is, it measures the strength and direction of a linear relationship between the numerical variables, which lies between -1 to +1. Positive correlation means if with increase in one variable there is an increase in the other, or we can call dependent variable, or any variable. Zero correlation means there is no correlation; they are independent of each other. Negative correlation, if one there is an increase in one variable, the other also increases. So sorry, negative correlation means with increase in one there is decrease in other variable. So this is negative correlation. So I show you the correlation matrix that we have got. So here we have is the correlation matrix for 2023. So it can be seen that like all the entries are significant, but it can be seen that the correlation entry between DIT and SIT is very high, like 0.924, and it is justified also because DIT is the degree centrality, while SIT is the strength of a node, which is weighted degree. So we had to drop one in order to avoid that multi-linearity issue. So we had to drop one. So we chose to drop the strength DIT, because strength captures the frequency, frequency of interaction also, key number of times the users are interacting. So it is capturing much more than what DIT captures, or so we had to drop one. So we dropped DIT. So this, all the entries are given by this formula. This is the Pearson correlation coefficient formula used to measure the pairwise correlation. Then I did statistical analysis using regression. I employed negative binomial regression as my data, my dependent variables, the variable count data. So I did that using negative binomial regression. So regression is the statistical technique where we model relation between dependent variable and independent variable, where independent variable can be more than one, where we see the effect of independent variables on dependent variables. So I had these many variables. So my um, equation looks like this. So I show you the models I worked with. So I had 6 models, where first model I took controls only. Like controls means badges, like gold badge, number of accepted answers, and this activity only. Then in the second model I incorporated strength also. Then third CIT alone, then KIT. In this way, then um, I calculated the BIC, VIF, BIC, and BIC is the statistical technique which tells which model best fits the data points. So BIC value, if we see, BIC is the statistical technique for model selection, and as the BIC gets lower, the model gets better. So BIC has to be the lowest among all the models. So I chose the model which had the lowest BIC, and it was the model that was incorporating all the all the variables, independent variables as well as controls together. So it was my last model that you can see having BIC value, this 3,39,675. So this was the BIC value that was the lowest among all. So this model was chosen as the best model, best fit for the data points. Then VIF was also calculated to make sure that there is no correlation among the independent variables. So it was restricted to be less than 5, and very luckily, so all the models had values less than even 2. So it was kind of plus point. So here is the mathematical um, insight via normal equation. So let's not go into this. So this is the network that I got and has been prepared in Gephi, um, which is a network visualization software. This is the network for December 2023, where node size is proportional to the repetition score, and the node color is as per the K-core. So here you can see the color palette where it shows the K-core index for like different K-core indices. We have different colors. As the K-core index gets like bigger and bigger, the color is getting darker. So in this way we see that how the repetition score is related to this K-core, how it is getting affected. So we can see there is potential correlation between them. So somewhere like pink is having K core 3, but it has like bigger size at some center of the network. It can be seen. So there is some potential correlation between them. So we were just to analyze the network. It was created. So now let's see what are the results and its impact. So it highlighted how structural position influences the innovation productivity of the user, and synergy of network structure um, and individual activity provided the most comprehensive um, explanation of innovation output. So, by analyzing the structural position and users' behavior, they can be they can be recommended for elevated roles also, like in the role of moderators and reviewers as per their contribution in the platform. So this framework is generalizable, and it can be generalized to other online innovation networks also. So before I conclude, I would like to say thanks to my advisor, Dr. Satya Mukherjee, for his invaluable guidance and constant support. I would like to, I'm very grateful for SciPy India team for this opportunity that they have given me. I also want to thank the Department of Mathematics and Shivnadar University. Without their support or their like all that they have provided so that I could carry out my research is just I'm very thankful for. So here are the references that I used in my work. Thank you.
Thanks, Monica. This was a nice presentation. If anyone has any questions, please feel free to ask right now, or maybe take the conversation offline somewhere.
Also, feel free to drop your questions in chat while the person is presenting so that we can always take that up during the question and answer section. Yeah.
Yes.
Yeah, hi. If I could ask a question, I think I just wanted to ask how easy or difficult it was to use some of the open source libraries.
Like it was very difficult and challenging as well, as due to limited computational uh, like power sources that we were getting, because we had a large XML file, or we had to like have like tackle these many files, or it was like very big data set, right? So it was kind of, it was challenging. It took whole 1 year kind of. So it was.
Yeah, thank you, Monica. I think just linking it back to what Agriye was mentioning at the very beginning, like, would it have helped if you had maybe some sort of software engineering training or scientific computation training? Would that have maybe helped you write your scripts faster and like maybe fasten up the process? I'm not sure if I was audible or not.
Oh, yes, you were,
Hello?
Rahul. Yes,
Oh,
you
okay.
were.
Yeah, okay. Yeah, it looks like Monica is muted. Not sure if she's having audio problems.
Right.
Yeah, I guess we can move on to the next speaker in the meanwhile. Thanks, Indranil, for confirming.
Am I gonna be speaking next or Manideep? Because Agriya was.
Manideep will be
Yeah. Okay.
the
Cool.
next speaker.
Cool. Yeah.
Yes. So, hi Manideep. I think we have around 22 minutes, just so that we're like um, on time for the next set of speakers. So please feel free to start when you're ready.
Yep. Am I audible?
Yes.
Oh, yes, you are.
And I hope you guys are able to see my screen.
Yes.
All right. So, hi everyone. Glad to be here. I'm Manideep Pendyala. I'm an AI researcher at Rutgers, US. So, first of all, thank you for having me, and thank you Indranil and Arigya for agreeing me to go second. It's 4:30 a.m. in the morning, so I really appreciate it. Um, my research is about AI-driven drug repurposing. So, just the technical terms aside, let's just focus on, the drug repurposing part. So we understand what, I'm trying to do and why. So, traditionally, medicines or any sort of drugs, they are created through a particular process that involves a lot of clinical trials and then FDA approval. And so this is basically a very time intensive process. It requires around 10 to 15 years from discovery to market. And I'm sure you guys are aware how expensive medicine is in the US. So based on some reports, it costs around 2.6 billion to create a new drug, and the failure rate is extremely because FDA regulations are very tight. Um, so clearly, this is a very limited return of investment. Not just in terms of financials, but also in terms of human effort. So a solution for this would be something called drug repurposing. So drug repurposing basically entails just using a drug that has already been approved by the FDA. So FDA is the government body that oversees all the use of different drugs and other medical devices. So the benefit of this would be simply that instead of going through all this extremely long process, if we actually use something that's already been developed for something else. So for example, I'm sure you guys are aware of Viagra. So it was originally meant to treat older patients with heart conditions, but now it's used for something else. So similar to that, there are many other examples like thalidomide or metformin, which are basically created for a different purpose, but their mainstream use currently is for something else. So doing this would reduce our development costs for drugs by almost like a one third, and it will significantly reduce the cost to make a new drug. And this is also low risk because clinical trials have been done, and and the drug is deemed safe for consumer use. Because and not just that, the manufacturing of these drugs are also simpler because the whole process is streamlined, right? So obviously I'm sure you guys at this point understood the benefits of drug repurposing instead of following the traditional new drug discovery route. So in this day and age of AI, we had a thought maybe we can use AI to help in this process. So instead of, let's say, we have 1,000 different drugs that we want to use for a particular disease, if we can use AI to bring that number down to maybe 10 or 15, that would really save a lot of time, because that's the whole point of AI, right? Like, just to make our lives uh, easier and just clear all that unnecessary manual background work. So this is an overview of our approach. It's I understand it's quite technical terms. I'll try to make it as simple as I can. Yeah, so we'll just follow a basic structure that everyone uses. So first, I'll describe the data sets. So so we need our LLMs. LLMs are large language models. Uh, so we basically need our LLMs to understand what different chemicals look like. So for that, we are using this data set called ChemBL. It's an open source data set. It's available at the given link. I'm sure it's in the reference section. So this basically tracks bioactivity data, molecular structures, and pharmacological annotations. So all the chemicals, each drug, they have a particular smile. It's a simplified molecular input line entry system, which is a textual way to represent a molecule's atoms bonds. And this dataset also includes bioactivity values. So IC50, to say in layman's term, would be a potency, like how the concentration of a drug that is required to inhibit a biological function. That means at what level it'll start showing it effect. So the higher the value, the better it is. So this data set is quite large. It has over 2 million compounds with 15 million activities and 13,000 targets. So this has like different compounds which can be which have different targets. So targets here are basically diseases. So we use multiple data sets. The second one we use is comparative toxicogenomic database. This is also an open source. It has a knowledge graph construction. So so the data set, it has disease IDs. So we use these disease IDs to merge our learnings from all these different data sets. And the same with PubMed. It's basically biological literature. That means research papers and all of it. So we chose to use this because obviously recent LLMs have incredibly high context windows. So providing additional context would add a lot of value. So what if you guys can see here? So we have ChemBL, we have CTD, we have PubMed. So what we have so far is molecular structures and their potency, how good they are. We have chemical disease associations, like how one particular chemical is associated with something else, and we have biological literature. So our task right now is to just combine all of this into a standard way so that we can feed it to our whole LLM pipeline. So all these three data sets are quite different in their representation. So we had to play around a lot with merging them into like a single unified index, because when you're dealing with such large scale three data sets, you need to have like a proper index. So that's why we created a master index dictionaries. So it will assign unique integer indices to each entity type, chemical, disease, genes. so that when we're doing inference with our LLMs, we can just provide that particular string, and the relevant information would be given to LLM instead of there happening a mismatch, which could be quite serious in our case, because we're talking about people's health here. So this integer index, it serves as a direct lookup into our various embeddings that we'll be using. So data pre-processing is pretty straightforward here. I'm not gonna go a lot in detail. We just perform our textbook things like just normalization and just create adjacency matrices. Because we are using CTD for graphs, we just use these associations to give weights to our nodes. And training test split, we decided on the split based on our experiments that gave us the best result. And the other data sets are also done in a similar way, but a little bit different because they are not the same type of data sets. So once we did this, so I'm sure you guys noticed that different data sets, they have different feature, like their basic use case for us is different. So for each of them, we used a different method to extract all these information. So basically how this thing works is we extract embeddings. Embeddings are basically vectors that LLMs or any other NLP method uses. So these embeddings will have all the information of the same data set. So for example, if we are talking about one particular disease from our master index, so it will have all sorts. So we will use different LLMs like Molbert, which is a modified version of BERT. I'm sure you guys are familiar with it. We use graph neural networks, and we also use DotLink to generate different types of embeddings. So the idea here is that when we try to generate different types of embeddings, they have different information related to our data. So that we can actually fuse them in our later stages and use it for our final model. So graph neural networks are basically a machine learning model that's designed to work directly on a graph structured data. Because our CTD data comes in the graph format, we were able to do that. So the input here is the edge list from CTD and the adjacency matrices we created. And the output would be a 128 dimension node embedding. That basically means it's just a vector, one-dimensional vector with 128 values in it. So this will provide us with the structural knowledge to the fusion layers. So models the indirect relationships and boost predictions where molecular or text alone is weak. And the next we use is Molbert. It's so for this we used pre-trained weights provided by a researcher. So this encodes the molecular structures into into embeddings. So this is a pre-trained model for all our LLMs. We used A100 GPUs. So this Molbert embeddings, they capture chemical grammar and activity. They predicts the potency from sequence and complements GNN for novel compounds. So I'm sure so far a picture is being painted. So for the same chemical, for the same association, we are just uh, getting different perspectives. We get from so far we got from the chemical structure, we got from chemical disease associations, and from Yeah, and also from the scientific literature. So all of this combined in form of embeddings, this would be fed into our final model. So the dot link, it's basic. It's a very basic, version. So it's a baseline predictor and adds an additional feature input. So so we use the dot link output as one of the metrics that we use to measure the how good the candidates are. So basically, we have all these embeddings. We just concatenate them and create a 1728 dimensional embedding, and then we pass it through a two-layer MLP, with radio activation. And so we finally have a 256 dimensional vector for our downstream prediction with multi-source knowledge. So basically, we combined all different types of knowledge that we can into this. So this one vector has information from research papers, from molecular structures, and chemical disease associations, potency values, and everything. So now we send it to the aggression. So aggression is quite interesting. Actually, it's quite new. Um, so aggression, it goes beyond predicting just the mean. So it provides a conditional distribution, uncertainty estimates, standard deviation, and confidence intervals. So it's actually inspired by the energy function. So we use the score matching loss with noisy samples at inference and integrate the values. So basically, aggression, similar to normal regression, it provides a proper full conditional distribution, which normal regression doesn't. So we got pretty interesting results. So the metrics that we use are RMSE, ECE, AUCR, ROC, and AUPRC. And precision at the right 10, it basically means that the fraction of correct predictions in the top 10 ranked results. So I'm sure you guys can see, the improvement by adding aggression and making our whole pipeline multi-modal. So multi-modal basically means that we use different types of inputs. So for example, if you create a pipeline that uses video and audio and text, that would be a multi-modal. So here, our data, we have like different um, perspectives of the same chemical disease association. So yeah, it's a multi-modal architecture. So we did a case study for a particular disease for which we gave an idea of this. So basically, when we send this particular disease to our model, it gave us like 8 drugs that can possibly be used as cure for this disease. So so the first and second drug, they have decent potency values. That means they have good effect. But the 3 to 5 ones are pretty high. So clearly, first one is not recommended because it has like quite low potency. 5.28 is nothing. The second one, it has moderate graph connectivity. It would make an excellent candidate. 3 to 5. So they have lower graphs. They're viable as a second candidates, but because we have a link score which we got from our dot link model, because it's I haven't added it here, but it's minimal, as in it's probably under 0.3. So because of that, they can be dropped out or used as a secondary candidates. So basically, what happened is, for a particular disease, from having thousands of possible drugs that can be used, we narrowed it down to 3-4. So companies can just um, perform their clinical trials and other requirements just on these 3-4 drugs. which would significantly reduce the cost of creating a new drug and the time for it. Yeah, so this is an example of how a potency distribution would look like. They're all just your normal distributions. So in conclusion, this unified end-to-end framework combining diverse biomedical data gave us a 13.3% performance over single modality, that is GNN only. And this uncertainty quantification is quite unique and and based on my recent research, it hasn't been used in this context. So so we think we have something pretty interesting in our hands, and we will. This research is yet to be published. That's why I'm not able to share any extra details on the code with you guys. But yeah, hopefully it'll be published soon. So this we actually submitted to a couple of conferences. And we plan to scale it up and submit to much larger conferences like NeurIPS or ICLR. And yeah, all the references, everything that we use is open source, other than our GPUs. Obviously, they're not publicly available. So yeah, if you have any questions, feel free to ask me.
Hi, Manideep. I have one question. It was a really cool talk. About the ingression, are you trying to minimize the energy function? Is that like a optimization problem?
Yes.
Okay.
So basically with ingression, what you're trying to do is, along with your normal values, it also gives you the uncertainty, right? So so it'll tell you like, okay, so let's say it predicts something. It predicts the association for like a particular drug and disease, and with ingression model, it also gives you the uncertainty of its own answer, like how certain it is. Like if you go to a Quillbot or some AI checker, it'll tell you like 100% likely AI. So this is just an additional metric that we can use to keep things focused.
Okay.
Yeah.
I see.
Thanks, Manideep, and thanks, Indra, for being inquisitive about his presentation. So I think I'm not sure if we'll have any other questions, and we don't have any on the live stream either. So maybe we can proceed with your presentation.
Okay, cool. Try to share my screen. Okay, you can see my screen, right?
Yes, and we have around 22 minutes, assuming
22,
that,
okay.
yep. So we have a lightning talk at the end.
Okay, so I'll try to keep it within 22 minutes. It's gonna be a hard job, but I'll try my best. Okay, thanks, Agria, and thanks the SciPy India team for having me today for this talk. I'm gonna talk about time series analysis for coupled neurons. So I'm not gonna assume that everyone knows what these terms mean. So I'm gonna, I'll take some time to go through these phrases throughout the talk. So I'm Indra. In short, you can call me Indra. That's my website. You can have a look if you're interested in what I do and like what's my background. I'm currently based in University College Dublin in Ireland, and that's my email. And I'll share the slides in LinkedIn. So if you have any questions or something like that, just shoot me an email. Okay, a bit about me. I did my bachelor's and master's in physics. That was in Kolkata in Jadavpur University till 2020 when COVID hit. And then I moved to New Zealand for my PhD in applied math. So I shifted my area of research a bit, but not by a big margin. It still had some similarities. And I finished in 2024, after which I did my first postdoc in the same university as well. And then I recently moved to Dublin in Ireland for my second postdoc. And this topic is mathematical neuroscience, which I'm going to talk about today. So as you can see, throughout the trajectory, my area of research became more and more niche. However, there was one glue that was Python. So I have always been a big fan of Python, and I've used Python for my work or research and this kind of stuff. The second thing is so although my area of research changed a bit, but I have been focused on dynamical systems. So I'm pretty sure everyone here knows the basics of what a dynamical system is, but I'm gonna describe this now. So there are different mathematical tools. I'm a mathematician, so I think in terms of mathematics, but it can be perceived using the tools from different other literature as well. So, but this talk is maths based. So I'm going to talk about ordinary differential equations. So Newton and Leibniz, they came up with this mathematical tool called ODEs, which can be used to analyze dynamical systems. So dynamical system is a system which evolves in time, in short, right? So there are other tools like partial differential equations, like stochastic differential equations, or like cellular automata, like different complex tools that you can use. But we're going to look into this simpler form today. So what it does is it studies the rate of change of a physical quantity over time. And when it can be, so the mathematical notation to denote a dynamical system is like this, written as x dot, which means a change in that physical quantity with respect to the change in time. So D denotes change. And physicists and mathematicians, they try out what this functional form is in their research. So they have a problem set up, they try to model the system using mathematics, using differential equations, and all they try to figure out is what if is. However, mathematical modeling is a bit tricky. As George Box said, every model is wrong, some models are useful. So people have been trying to, in terms of neurons, model the behavior of neurons using ODEs for a long time. So I'll talk about that shortly. But before that, what's a neuron? So neurons are the fundamental units of our nervous system, which makes us do our day-to-day job. It's the reason why we are what we are. So there are billions of neurons that couple through this structure, which has been denoted in blue. So just to make sure I haven't drawn this, I've stolen this from this particular website here. It's a pretty cool website. You can just go and learn about neurons from this website. So what it does is synapse is a bridge between two neurons. So a signal is propagated from the presynaptic neuron to the postsynaptic neuron, which is the second neuron, or you can just call it the first neuron and the second neuron, through the synapse. So it just takes the signal from the first neuron and propagates it to the second neuron. And this mechanism evolves over time. And it's just two neurons here, but the brain is far, far more complex, and it's built of a neural mass. So this can be perceived as a dynamical system. And one particular topic that I'm very much interested in studying is chaos. So what does chaos mean? Chaos in dynamical systems. So when you plot this system over time, most probably will come across a state of disorder. So that's what in popular term chaos means. In mathematical term, what it means is this happens due to very high sensitivity to the initial condition. So every dynamical system, when you try to study it, you need to have an initial point to start the simulation, or like to study the system, right? So a slight perturbation to that initial condition will, like, vastly change the end product of the whole simulation, or like the whole dynamical system. So that's a signature of chaos. And also, if you plot some of the variables of that system on a 2D space like this here, you'll see that like the space gets filled up pretty easily, like pretty fast over time. So that's what it means, like a dense orbit. It's a very like common example from double rod pendulum. I've taken this from this website in Medium. Again, a very good description of what chaos is. Just have a look. So chaotic systems behave predictably in the beginning, but as soon as the system like evolves in time, it starts behaving randomly. So that's what a chaotic system is. Okay, so this is a Python talk. Different packages that I use for analyzing neurons and like chaos in neurons. The first one, I'm pretty sure everyone knows what NumPy is. It's for numerical algebra, or like numerical like nitty-gritties in Python. This is the core package of this conference as well, SciPy. So the scientific suite of Python. The third one is pandas. We are, in a way, all scientists are data scientists. I would say everyone works with data nowadays. So you need to process the data, and pandas is the best tool to do that, I would say, in my as far as I know. And finally, for visualization, we need Matplotlib. So the 4 core packages that I use almost every day, at least 1 hour. So for 1 hour. So yeah. Now neurons. So like we can. So as I was mentioning before, there's a huge plethora of models that simulate the behavior of neurons over time. But what researchers do is like they try to come up with better and better neurons, like empirically informed better and better models, which are more empirically informed, right? So I've taken a pretty like a recent model from 2018 by Schaeffer and Kane. You don't need to know what these equations mean, but just to give you a flavor of what I'm trying to do here, like here X is denoting the voltage of a particular neuron, Y is the recovery variable of that neuron. So what happens is, like, when a neuron fires, so after it fires, it needs to come down, right, before it can fire again for the next set of time. So Y captures the recovery of that particular neuron. And I here is from your physics class. I don't know if it's the same notation used, but I have always used I for current. And this is the external stimulus current that stimulates the neuron, and it changes very slowly over time. We plot so it creates, when you run the simulation, it creates synthetic data, right? So I'm not talking about data that you collect from like experiments. Here I'm just going to talk about synthetic data. So when you run the experiments, you have the voltage data that you plot against time. Oh, sorry. And that's how you get the time series. And you can also plot the voltage against the recovery variable, and that will give you the phase portrait. So these are two, in dynamical systems line of research, these are the 2 most important plots that you will see, like that you will come across all the time. So this model captures realistic bursting in neurons. It portrays a battery of complex dynamics. And again, this is a Python talk. So just to focus on what functions or functionalities I use from the package, I've used solve IVP. So IVP denotes, so it's the short for initial value problem. Oh, I just have 10 minutes. Okay. So what it does is, like, it solves a dynamical system with a one-liner, and it's from SciPy.integrate suite from the SciPy package. So just translating that to Python initial conditions. Okay, and then you specify the time span. So how long do you want the simulation to run for? And then you also need to specify the number of timestamps. So that's 50,000. And that's the one-liner that solves the differential equation. You extract the solutions, and then you just plot it. Now that was just single neuron. We move to double, like a coupled neuron. So just looking into two neurons now coupled through a synapse. The synapse can be two kinds. The first one, actually, synapse can be like multiple kinds, but these are the two mostly studied kinds. So the first one is like electrical synapse, which is very straightforward. It's like the transmission of electric, like the synapse. The transmission of the signal propagation is bidirectional. So that's why you can see like there are two arrows indicating on either side. When it comes to chemical synapse, it's a bit trickier because it only propagates from the presynaptic neuron to the postsynaptic neuron, because the propagation happens through chemicals, which are called neurotransmitters. You can see here the round ball-shaped objects with dots inside it. So the dots are like neurotransmitters which get released at the synapse. So just converting the physical, like the biological phenomena to some toy models of coupled neurons. This is the electrical coupling, also called gap junction coupling. So now we have two neurons, the red and the blue, connected by the coupling strength, which is theta. And that's the coupling term which captures the bidirectional coupling. When it comes to chemical coupling, it becomes a bit more complex. Not that much, but it's a bit more complex than the electrical one. You can see, I'm pretty sure everyone can tell what this function is. It's the sinusoidal function. So it captures the more non-linearity in chemical coupling, and that's how mathematicians model chemical couplings. And then move to a more hybrid electromagnetic coupling, which is it takes into account the electrical version and also some other kind of non-linearities which comes into effect. It can be modeled using some electrical components, for example, memristor. So there are capacitors, inductors, resistors, and the fourth object is memristor. And I'm not going to talk too much about it, but you can build this literally in an electrical lab. So again, like translating all those toy models in Python, I've just changed the function that needs to be written down. Very straightforward. Okay, so 4 minutes, I'm going to talk about time series tools. So now that we have the data set, like the synthetic data set from all these models, we need to analyze the data, right? So to do that, it's a time series data. So to do that, we have 5 different statistical measures that you can use. The first one is Hurst exponent. So it measures how persistent the time series is. I'm going to explain this soon. Sample entropy measures how complex the time series is. Then 0-1 test for measuring how chaotic the time series is. And then cross correlation function. I think you saw this in the first talk, which measures how two neurons synchronize with each other over time. So this is a very important topic that people study nowadays, what's the purpose of synchronization in the neural mass. And similarly, there's another order parameter that you can use to study synchrony in neurons, but in terms of phase, not voltage or like recovery variable, but you can translate it into a phase dynamics framework. Okay, I'm not going to talk too much about the maths behind it, but what Hurst exponent does is it captures the expected value of the ratio between two functions of time, and it measures how fast it grows in time. So here age is the exponent, and it lies between 0 and 1. If it lies between 0 and 0.5, that means the time series is anti-persistent, which means at a particular timestamp, if the trend is to go up, in the next timestamp, it can either go up or go down. So there's a negative dependence on previous values. So that's what anti-persistence means, and it somehow relates to chaos or complexity. When h is 0.5, it's a random walk. When h is otherwise, then it's positive dependence. So like if at a particular timestamp, the trend is to go up, in the next timestamp, it will also go up. Sample entropy, it captures the complexity of the time series data. It's a probability based measure, and a higher sample entropy, it indicates higher complexity, and it can be normalized between 0 and 1, but you don't need to. So this gentleman, Shoel, from 2019, he wrote a package called NOLS, which is a Python package based on NumPy. It means nonlinear measures for dynamical systems. It provides options to like implement these nonlinear measures on time series. You can find the Hurst exponent calculation and also the sample entropy calculation through these two, like, one-liner functions. So it's very straightforward. You can also use the 0-1 test to see whether the time series is chaotic. It lies between 0 and 1. And you can, so there is a step in between to translate the voltage variable and the recovery variable to P and Q variable. And just plotting this, you can see whether the time series is chaotic or not. I can show you one example. So for the 0-1 test, there's a package written in Julia. So we needed to translate it into Python way before ChatGPT. So it was like 2.5 years back. So yeah, ChatGPT was there, but like it was not that good, I would say. So we still needed to have our oversight. I would still say like you should always have your oversight when you're saying like, using ChatGPT. But anyway, I don't want to go into a rant about that. So we used like curve fitting function and like the root finding function from SciPy.optimize suite. One of the steps, you also needed to use Pearson's correlation coefficient function, which is Pearson R, to compute the measure. And it comes from SciPy.stats. So you see, like my research is very dependent on like Python and the open source software package. So cross correlation coefficient, it just measures how two neurons are synchronized with each other. If the absolute value is 1, that means it's total synchrony. If it's not, that means it's asynchronous. So it's a very small set of Python code that you need to implement to study cross correlation coefficient. This phase translation as well, I don't want to talk too much about it, but it also captures how two neurons are synchronized with each other. So some results from the electrical coupling, which is also called the gap junction coupling. You can see I'm plotting with respect to theta. So theta going from my like negative value to a positive value. So negative theta means like one neuron is inhibiting the other neuron, and positive neuron means like one neuron is exciting the other neuron. So when there is an inhibitory behavior, you can see like the translated variables gives a very random kind of walk, which means the two neurons are behaving chaotically. You can also see from the time series. That's my time. I'll take 2 more minutes, I think. Okay. So the time series is like chaotic as well, which is captured by the value of k, which is very close to 1. The Hurst exponent is anti-persistent because it's less than 0.5, and similar kind of behavior you can see here. This is for theta negative as well, but a slightly higher value than the left plot. So it's becoming more organized. So k is decreasing from 1. However, the Hurst exponent is still less than 0.5, and so it's anti-persistent. And you can see here the sample entropy values for both of these are very small, very high. So that means like it's more complex when the coupling strength is inhibitory. And again, the two neurons are asynchronous because gamma is far away from having the absolute value 1. So, but when theta becomes positive and like one neuron excites the other neuron, you can see there is more regular behavior. So k has like decreased quite a lot. It's close to 0.15 or 0.16. Hurst exponent has increased, so there is like persistence behavior in the time series. Sample entropy has decreased as well, so less complexity, so more boundedness, more regularity. And also the two neurons have synchronized pretty well, so they're very well synchronized. And you can see the bursting behavior. So if one neuron is bursting, it will excite the other neuron to burst as well. So similar things happen in chemical coupling and the electric coupling, but there are other intricacies that come into effect. I'm not going to talk too much about that now. I don't have time. You can also plot those behaviors, those metrics with respect to theta. And this took quite a lot of time for me. I'm going to talk about how to optimize that. But one PSA, I would say, if you're into analyzing data set, like running simulations and analyzing data set and like creating visualizations, always try to separate the experiment from visualization. Don't do it in one code block, because I know it's very people tend to do that, but on the long run it will save you quite a lot of time. So it's an inspiration from a talk that I heard from Tammy Calder. She's a mathematician by training, but she has her own AI company, I guess, nowadays. And like it was she was a keynote in a maths conference that I attended last year, and I was taken away by her talk. It's really good. So this is the code that creates the data files for my experiments, and this is the code, like I then read the data set back and then feed it into matplotlib to plot all the plots that you saw previously. So summary, okay, I took one more minute. Okay, summary is like I used Python to study coupling and how it induces chaos, and all the behaviors that you saw. So in terms of future work, I want to move the study to a GPU accelerated framework. I came across this package called QPy. I think Q is short for CUDA. Correct me if I'm wrong, but yeah. So that's my next goal. And also, I want to move from using 2 neurons to a neural mass where like the number of neurons is like more than 10,000 or something like that. And you need to inculcate the knowledge from network X. We saw a flavor of this in the last 2 talks, I guess. So, and network is very important. Acknowledgements, these are my collaborators. We are spread across like Europe, New Zealand, and India. That's the reference. This is a tutorial paper. This talk is based on this tutorial paper, which is still under review. Hopefully it gets accepted soon. We recently submitted our first review. And if you're interested in the Python code, have the paper ready by your side, like your side, and then also go through the code, which is openly available in the GitHub repository. So that's it. Thank you so much. Any questions? I hope I'm meeting. What can I say? I can't find the. I don't know where to.
I assume there are no questions.
Okay.
Yes.
How do I stop sharing? Can't find the.
I think maybe I can do that for you.
Okay, cool.
From
Awesome.
my
Okay,
end.
I can't find the GC at all. So, yeah. Yeah, if you have any questions, just send me an email or something like that, or in LinkedIn. So, yep. Thank you.
Thanks, Indra. So I think our next speaker on the lineup is Mridul. Mridul will be talking about sktime.
Yeah, so am I audible?
Yes.
Okay, so share my screen. Cool, cool. Yeah, is my screen visible?
Yes, it
Yep.
is. So I think we have around 20 minutes because we also want um, some part of the presentation at the end to incorporate our closing notes. So just um,
Yeah,
yeah.
yeah, I'll be finished under 20 minutes. Okay. So, hi everybody. Thank you for having me. And I'm Mridul Jain. I'm a recent graduate from VIT Vellore in India. I'm a developer and I'm also an open source contributor. So I've recently worked with organizations like PGMPy and sktime. These are two open source organizations. And today in this talk, I'll be talking about sktime and how sktime is the go-to tool for you if you want to perform time series forecasting. So in this talk, I'll be talking about the hierarchical and probabilistic forecasting, but then in general, I will also talk about what, why do we need forecasting and what is SK time, how can we use it, and also in the last, I'll be sharing a code sample on Google Colab to like show you in practice how we can perform forecasting for any hierarchical data. Cool. So what is SK time? First of all, SK time is an open source package or library for time series analysis, right? It provides a unified interface for classification, forecasting, regression, clustering, and also transformations. So you can basically think of it as like a scikit-learn for time series operations. So its modularity or its API design is all compatible with scikit-learn. And then lastly, it ensures consistency across models and tasks. And why do we need ASCII time? The answer is very simple. We, since we have time series datasets everywhere, from sales to energy to finance and healthcare, we need to handle and we need to perform operations on these time series datasets. So ASCII time is one of the possible options we have. Then we have this fragmented ecosystem where tools like Arima, Profit, and Scikit-learn have inconsistent APIs. So sktime, what it does, it tries to unify everything. So it will include all the forecasting models, and also it will try to make consistent all the APIs and provide a single interface which has modular design, and it also has seamless interoperability. But now I want to switch my focus towards the forecasting part. Now, what is forecasting? I'll take a step back and I'll describe the basic attributes of forecasting. Now, forecasting is predicting future values from the past data. So, in a time series data set, what we have is we have trends. Trends could be trends could be any long-term growth or long-term decline, which we can observe. Like for example, if the stock of a company which was increasing for the past for the last 10 years, but right now it's in a declining stage. So that's a trend which is going on with that company, right? And then we'll talk about the seasonality. Seasonality, it's basically the repeating pattern or cycle that occurs at regular intervals. It is the predictable wiggle in the data, which is caused by periodic effects. For example, we can see the retail sales spike every December. Website traffic drops on weekends, or maybe electricity usage peaks in the summer. These are all simple examples of what we call seasonality. Then, lastly, we have noise. Noise is, I guess, the random, unpredictable part, the stuff that doesn't follow a pattern. It's basically the leftover variation after you account for trend and seasonality. For example, the random daily spikes in sales due to unplanned events like a viral tweet or a power outage, right? So it's basically the residual component, which we often assume as the white noise. So coming to the forecasting methods, we have many methods, but primarily we encounter these four methods. The first one is the knife. The second is exponential smoothing. Third one is the ARIMA. And the lastly, we have ML based methods for forecasting. In my code example, I'll be talking about exponential smoothing and how we can use this model to forecast the values over some specific seasonal period, right? Now, what are the challenges we face during forecasting? Uh, so you can see the one forecast is not actually enough for real world needs. So the real world data sets, they're actually kind of messy and they're kind of fluctuating. You can't have a single monotonic patterns being followed in the real world data sets. So a single forecast does not make any sense in that context. And then the different stakeholders, they want so many plannings. They want to plan for short term as well, for long term as well, for medium terms, right? So that depends upon the stakeholder. But for short terms, we have the operational planning. The medium terms could be planning the budgets and the marketing part, and the long term could be the strategic decisions which the company needs to take, right? So forecasts must often work across multiple levels. You can't have a single level forecasting because that's what we are facing the challenges in. We are having these real world complex scenarios where multiple layers of forecasting which aggregate to one specific answer. That answer is what we want, right? And that leads us, and this kind of data, these kind of layers, they lead us to practice hierarchical forecasting. Now comes the hierarchical forecasting. Imagine you are having a company, right? And you want to basically find the sales of the company. So what you do is you basically have these data sets which are segregated into different components, different layers, different levels. The first one is the regional level, where you have the region sales. The second one is the store level, where you have the sales at every store. And then third one is the product level. So you basically have the numbers of what our products have been sold. And then you can also take it as a country level sales, a state level sales, a city level sales, and a household level sales, right? So you kind of add up, you kind of go from top to bottom. You kind of uh, minimize the range, and then you perform the forecasting on that specific small range. And then eventually you come up towards the higher levels, adding all the forecasts together and getting a final answer. That's the basic math which we have in the hierarchical forecasting, right? So as you can see in the figure on the right, what we have is we have a total value, and this total value has been split into A and B. And then the A is having forecasts as A is having the subchildren as A, B, and AC, and B is also having subchildren as B, A, and BB. So yeah, this is the basic concept of hierarchical forecasting, and it has many use cases in the real world scenarios. Now let's talk about why hierarchical forecasting even matter. So the first is it ensures forecasts are coherent. They're consistent across all the levels. So uh, a simple example to explain to explain this point is uh, if you manually sum up the sales from the region levels altogether, then you also calculate the state level sales, and then if the state level sales and then the regional level sales, you can see the numbers don't match sometimes. That is because uh, there are some external or internal factors which influence the sales and which lead us to a wrong answer, which we do not want, right? So hierarchical forecasting, this ensures forecasts are coherent, and you don't have any scope of error in any of the levels, in any of the calculations. So it aligns planning from executives to regional managers to local stores. right? It improves accuracy by sharing information across all the levels, and it has a plethora of applications. Could be supply chain, could be energy distribution, could be financial reporting, and so on and so forth, right? Now comes the probabilistic forecasting. But before this, I want to go back and I want to show you the code snippet. Like, how do we use sktime to perform this hierarchical forecasting? So as you can see, I have the NumPy, I have the pandas. I'm using sktime as my Python package for performing the forecasting, and I have the data. The data is basically manually created just to get a feel of how a hierarchical data looks like. So as you can see, we have the periods could be and the number of periods are 36, and also we are first creating a A1 series data. That means we are using the multi-index in the pandas, and we are fixing we are having a range of dates, right? Similarly, we have the A2 level, we have the series A2 dataset, the series B1, and the series B2. Now, the next step is, of course, we need to aggregate these individual datasets. So what we have is we take another series A dataset, and then that is basically the summation of series A1 and series A2. And then similarly, we have series B dataset, which is summation of series B1 and series B2. Similar to what we similar to what we had in this triangle. This is the series A dataset and this is the series B dataset, right? So we're working upon a similar idea, and total would be the summation of series A and series B. Now, for example, I've printed the series A dataset, and this is the basic. Uh, this is how the series A dataset looks like. So you have a range of dates, and then you have values, and this is basically across all 36 periods, right? And now we convert this to a pandas data frame because we are easier to work with. It's easier to work with pandas data frames. So we convert this to a pandas data frame in the form of table. We print it, and we can see the total sales, the A1, the A total A, the total B, and then the individually A1, A2, B1, B2 data sets, or the list of values, right? Now, we need to perform hierarchical forecasting, and we need to use a forecasting model. So in this case, I've used exponential smoothing. Now, exponential smoothing is basically, I would say, better in some cases than ARIMA. ARIMA is also very nice, but it kinds of turns functions complex, whereas exponential smoothing is easier to work with. And yeah, so first, what we do is we kind of import the API or import the class exponential smoothing. We try to define the forecasting horizon. Now, in this case, the forecasting horizon is basically from the range 1 to 12, and it forecasts 12 periods ahead. And then we store everything into a dictionary. A dictionary, we are calling it as forecasts. Now we go, now we traverse through the columns, and we take the current column, and then we apply the forecaster, the exponential smoothing forecaster, in which the arguments would be the trend, the seasonality, and the SP, which is the seasonality period. And in this case, we have taken the value as 12, right? Now, SKTime provides this very good functionality of fitting the forecaster on the column, so it's kind of a really nice way to do it, similar to what we have what we have in ML based approaches, where we are simply fitting the maybe supervised machine learning model on the X on the Y train, right? So it works upon a similar principle. And then we have the Y predictions, and it also provides a similar API, a similar method of predicting the values over this forecasting horizon. And then you can simply append this Y predictions value as a column to the forecasting dictionary or the forecasting data frame, right? After we are done with this, we're simply converting this forecasting dictionary into a pandas data frame, and then we are storing it in a variable. And as you can see, in the output value, the size of the data frame is 12. Of course, because we had taken the seasonality period to be 12, and it's across the 12 periods ahead, 12 years ahead. And then this is how the head of the forecasting data frame looks like. We have the dates, we have the total values, we have the a values, the a1, a2, and the b values, and which is basically summation of b1 and b2. So this is how exponential smoothing model works, and there are similar models which one explore in the sktime documentation. And now comes the visualization part, in which we're simply using this plot series method, where we want to plot the hierarchical data frame of the specific column, and then correspondingly the forecasting data frame of that specific column. So we can see the the difference between the hierarchical values and the forecasting values of every column which we have in the data frame. Like, the columns would be total a1, a2, b1, b2, right? And it's simply the visualization part. So as you can see, um, from the dates, from the months 01 to the month from 2020 January to 2023 January, what we're going to observe is the values are between 260 and 280, right? But then from 2023 July, the values have started decreasing. The total sales have started decreasing. And then similarly, you can just observe the patterns for the individual levels, the A level, the B level, and then individually you can just look for A1 and then the B1 levels, right? So this is how the basic idea works. And yeah, there are some metrics as well which I want to talk about. So this is basically another API under the sktime package, the performance metrics. And under that we are talking about forecasting. So basically we import the mean absolute error, the mean squared error, and the mean absolute percentage error. So we define the forecasting horizon again. We're splitting the data into testing and training part. We're defining a key metrics dictionary, and then for all the columns, we're simply applying the model, fitting on that, fitting on the data, predicting the values, and then we're simply calculating the metrics. So we have all these methods which are defined in the sktime, and simply we need to pass in the arguments, and we can simply store the values in a variable, and then you can simply append it as a dictionary or maybe as a data frame um, inside the metrics variable. So after printing this metrics variable and like rounding the values to 3, we can see the values of MAE, RMSE, MAPE across all the individual data lists, data sets. So for total for A1, A2, B, B1, B2. So yeah, I'm pretty sure you got the overall idea. What are we trying to achieve here, and what are the gaps we are filling by using sktime? Because time series predictions or time series forecasting, they all have very high demands in today's industries, right? So now I'll talk about the probabilistic forecasting. Now it's a very small idea. It's a very small depiction of what problems we are facing. So I've spoken this before also. We are talking about the point forecasts, but the point forecasts are not ideal, or they are not compatible with the real world scenarios. They are limited in nature. For example, if a company says next week we'll be able to sell 500 units, I mean, you can't basically specify a number for the next week, because you never know, and uh, that's very wrong, and that's very misleading in terms of predictions. So a better way to basically state this is like there is an X amount of percentage that we will be doing a Y units sales next month or next week. So that is the whole idea of probabilistic forecasting. You basically have probabilistic values which you have in as your answers, so that there is a kind of an idea, what number is most likely be the target value in the next range. So that's the whole idea of probabilistic forecasting. And of course, the real world is uncertain, so you need to have ranges and distributions. And this kind of forecasting, it helps with the risk aware decisions. For example, you can have safety stock, you can keep buffer capacity, and also you can do scenario planning for the future, right? Now, hierarchical plus probabilistic forecasting in sktime. Sktime supports both the approaches. Hierarchical forecasting, which involves many of the reconciliation methods, and probabilistic forecasting, which has all these prediction intervals and distribution forecasts. So you can combine them. You can have forecasts that are both consistent and uncertainty aware. So basically, if you are running a company, then you definitely want to check out, you definitely want to calculate the probabilistic forecasting, because you need to then tune your budget according to that. And you can't have any single number, because you can't, that because the likelihood of touching that number, or maybe keeping the sales around that number is very less. So you need to have probabilistic ranges, and that's where the probabilistic forecasting under time helps you a lot. And as you can see, the companies adopt this approach, and this approach is pretty scalable, practical, and also it's very Pythonic. So it's easier to understand for the developers as well. Lastly, I would like to end this talk by mentioning some key takeaways. So in this talk, I've talked about sktime, which is unified open source toolbox for time series machine learning operations, right? I've talked about forecasting basics, which is the trends we notice, the seasonality, which is there. That means the recurring pattern, the noise which we observe, and the point forecasts, right? Next, we touched the topic hierarchical forecasting, which is basically having data in multiple layers and multiple levels, and then you need to have consistency across each level, right? And then also shared a code sample of how we can use exponential smoothing under the sktime to perform some of the forecasting with company. You need to have some kind of range, some kind of prediction range, so that you can tune budget, or you can tune your resources according to that, and you can smartly plan for the future. So that helps you take decisions and being aware of the uncertainty that might arise in the future. And lastly, together these make forecasting realistic, actionable, and trustworthy. So some of the references I would like to mention: the sktime GitHub and websites. You can basically check it out from the PPT, and also the hierarchical forecasting. So there is a whole documentation on hierarchical forecasting, which includes global and panel forecasting as well, which you can definitely check out. So thanks a lot. My talk ends here. Thank you so much. So if there are any questions, yeah.
Yeah. I don't see any questions on the stream or also in the chat, so I think we can move on to the next talk. Thank you, Mridul, for the talk. And if you have any questions, you can reach out to him. And let's move on to the next talk by Abhijeet Mote on Mojo and AI, the future of Pythonic performance. So, over to you.
Thank you, Aditi. Can you see my screen?
Not yet.
How about now?
Yes, I think
It's
it's still popping up. I think it should render. Yep, works now.
Okay, perfect. So I just changed to the slides. Slides are visible, right?
Yes.
Okay, perfect. Thank you. Hello, everyone. Thank you for giving me an opportunity to present this topic. Uh, like I was just exploring about this Mojo just few weeks back, and I thought, okay, I can give a talk. I'm first time here on this uh, channel and SciPy community meet. So I'm having 12 years of experience, mostly into Python and data related field. I like to explore different stuff and apply those things into my uh, day-to-day life. So I came to know about this Mojo library recently, and still exploring on that one. Okay, so most of us here use Python every day for AI or scientific computing. Is the glue behind NumPy, SciPy, PyTorch, TensorFlow, you name it, and and it works so well because it's easy to write, easy to share, and easy to prototype with. The problem with Python is it is slow. When you want to train at scale or write a custom kernel or optimize a pipeline, you usually end up dropping into C++ or CUDA. Suddenly, you are maintaining two versions of your code, and one in Python for research and one in another language for production. So Mojo is trying to close the gap. It looks like a Python, feels like a Python, but compiles down system level speed. The idea is keep the productivity of Python, but the get performance close to C++. And today I'll walk through what that means. With a quick demo, look at reproducibility interop with Python and where this language might be heading. So let's start with the pain point. Python is fantastic for productivity, but because it's interpreted and dynamically typed, you pay for that convenience with speed. That's why under the hood, NumPy is really C. Python has C++ and CUDA kernels. Even pandas learns on compiled code. The moment you the moment you need something that doesn't already exist in libraries, like a custom ML kernels or specialized pre-processing step, you end up writing in C++ or CUDA yourself, and now you are maintaining two stacks. That's the problem Mojo is trying to solve. So what is a Mojo? In short, it's a superset of Python. Most Python code will just work, but it also gives you things Python doesn't. Static typing, low level memory control, parallelism, hardware level access. And because it compiles, you can get performance closer to C++. The goal isn't replace Python, it's to extend it. So you can keep your existing ecosystem, NumPy, PyTorch, SciPy, and just drop Mojo where you need more performance. Mojo is built with AI accelerator and heterogeneous computing in mind, meaning it can target GPUs, TPUs, and custom chips efficiently. As AI models grow, like a trillions of parameters, we are having multimodal reinforcement driven things. Efficiency in both and interface becomes non-negotiable. So this is Python. Like the right side is Python and the left side one is the Mojo one. So if you see, it's like very much similar, like how you define any function, and you just like there are some annotations. If you see, similar to like C or Java way. So the difference isn't in how you write it, but in how it runs. Mojo compiles this down to optimize code. So across millions of values, it's significantly faster. This is a toy example which I built, but the idea scales. Imagine pre-processing a large dataset or writing a custom kernels for ML models. You can do this in Mojo without leaving the Python ecosystem. So point here is almost identical syntax, but compiled much faster. Transition is one part, but the scientists also care about the reproducibility. So I'll show you some syntax and the performance gain here. So if I want to show the next slide, this is before that I'll show you how to run this one. So this was one of the example. And there is more thing, like we can have the compiled version also. So it when you compile this, it will create a .so file. So we'll see 2-3 examples here. So this is one Mojo file which we have the same syntax, and with the Python the same syntax. When we run this and the performance, you can see the Mojo is like almost 2.2 times faster. Like it uses less CPU than the like a page reclaims. It has 829 page faults is very less compared to the Python one. So then again instructions retired. If you see, like Python executes 148 times more instructions, so it uses more CPU. Then like 74 times more CPU here, if you see, for the same task which we have seen here. Okay, so performance is only part of the story. For AI and scientific computing, reproducibility is a critical. Python's ecosystem has spent decades improving packaging, from fragile requirements.txt to pips resolver, conda, mamba, pip 517. So build isolation and log files like pylog.toml file. We even now have GPU, CPU specific builds and SIMD, like single instructions, multiple data, NML builds. Mojo inherits this ecosystem rather than reinventing the wheel. Because it's superset of Python, it can fit into existing workflows, Conda environments, Docker containers, and log files, which means reproducibility for experiments and ML pipelines achievable. This is essential if Mojo is to be trusted in science. So another strength is interop. Instead of forcing you to switch ecosystem like Julia, Mojo is designed to interrupt directly with Python. We'll see the example how it is. So the vision is write a function in Mojo, compile it as a Python extension, and then import it directly. That's already documented through, though not fully in the open source toolchain yet. But I have created one demo version here. So today you can still run Mojo standalone or all Mojo binaries from Python subprocesses. That's enough to accelerate the bottleneck functions without leaving your existing NumPy or PyTorch workflows. For example, you could keep your PyTorch training loop in Python, but write a custom data pre-processing step or action function in Mojo for speed. Let's see the example here. Okay, so what I have done here is I have written this factorial function into Mojo, and I try to import this into like Python file. So what we have to do is we need to write the Mojo code first, and then we need to compile this and create the SO file, and then this SO file will be imported into this Python file. So if you see import a mojo.importer, and then here we need to give the path for the file. So I have kept this SO file into directory. So just give the current path. It will take, and then my mojo dot factorial function. So this factorial function, if you see, it is defined here, and then I'm just passing the argument from here. So importing that factorial function and running into the Python. So this way you can write this Mojo code like whichever is taking more time or performance heavy. So those kind of code you can write into the Mojo, uh, create the compiled version of that file and import it into the Python, which will really help you to solve these performance issues and gain into it. Okay. So so looking for there are few important areas to switch: packaging and reproducibility, better log file, and environment integration will be a key. Accelerator support. So Mojo is built with GPUs, TPUs, and SIMD in mind, which makes it especially relevant for ML workloads. Adoption, Julia showed the demand for the performance in science, but struggled with the ecosystem lock-in. Mojo is advantage is compatibility with Python, which could make adoption smoother in AI and scientific computing. So few takeaways from this is like a Mojo is superset of Python. You can run Python code directly. Adds types like parallelism and compilation. Allows you to hit C++ rush level speed. Best for both worlds, like easy to learn like Python, powerful like system language. Eliminates the Python versus C++ split in the frameworks like PyTorch and TensorFlow. So you can import Python libraries, but replace hot paths with the Mojo kernels as needed. So in short, Mojo is shaping up to the plus plus for AI, keeping Python accessibility while unlocking HPC performance. If successful, it could become the backbone for the future AI systems. There is one more thing I want to show is like we have seen from importing the Mojo into Python, we can do other way also. Let's say you have Python function and you want to import that into the Mojo, so you can do that also.
Uh,
Hmm.
yeah, sorry,
Hello.
it's a little bit over time, so I thought I'll interrupt.
Yeah, I'm done. Yeah, I was just showing this example. Yeah. Just to give idea, like these are like libraries from Python. Like in toml file, I have added that. Here it is. So pandas numpy already. So we can just use this syntax to utilize this. All right. Thank you. So to wrap up, Mojo isn't about replacing Python. It's about extending it. It keeps like Python's easy to use, but adds production level performance and reproducibility. So if you are curious, I encourage you to try the Mojo playground and experiment with small ML or scientific workloads. Yeah, thank you.
Thank you, Abhijeet. I think we can try and take questions later, but yeah, we can probably stop the recording now and just have a conversation. If people want to hang around, um, discuss any of the talk that happened. Yeah, Aditi, can you please talk about the feedback form and everything else?
Yeah, like it's a really short feedback form, and also if you think it does not cover all the aspects of a community call, you can just stay back and, or like right now only, you can give us some feedback on like how we can improve these calls or get better outreach, because like there are not a lot of people here. So yeah, and if you have any other feedback, you can like give us, and we'll try our best to like implement that. And yeah, if anyone else has something more to add, Agriye or Malayaja.
Yeah, folks, if you could fill out the feedback form, it will be really helpful for us as a reference for future community calls and even the conference, if that's something we are looking forward to. And I'll also be pasting the YouTube link for this live stream. So if the speakers here want to add it to their profiles, you can. I think this will be up on this channel, so you don't need to worry about it getting triaged of any sort. So or archived. But yeah.
And also a little plug that the feedback form is completely anonymized. So we don't bite. If you have negative feedback, please feel free to share with us.
Yeah, I'll just go ahead and stop the stream now so that we can have hopefully a much more candid conversation, if that's okay with everyone. Going once.